Good day, everyone, and welcome to the DOE Fuel Cell Technologies Office monthly webinar series. Today's installment, we'll be discussing HydroGEN's electrolysis capabilities. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our EERE website in about 10 days. We will send out an email to attendees once those are posted to the site. Next slide, please. Hewen, can you go to the next slide, please? Oh, thank you. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Next slide, please, Hewen. With that, I would like to introduce our DOE host, Ben Quar, joining us from the Department of Energy headquarters in Washington, D.C. Ben is a fellow supporting the Hydrogen Production and Delivery Program within the Fuel Cell Technologies Office. Good afternoon, Ben. Take it away.
Thanks, Chris, for the intro. And welcome, everyone, and thank you for joining the second of 3 webinars that will describe the capabilities in each of the water splitting pathways covered by the Fuel Cell Technologies Office HydroGEN Consortium. This webinar will focus on capabilities relevant to low and high temperature advanced electrolysis. Today we have the pleasure of having Dr. Hewen Din with us. She will describe the opportunities and capabilities for electrolysis materials research and development within the consortia. Dr. Hewen Din is a senior scientist and project leader at NREL. Dr. Din is the HydroGEN EMN director and lead for FCTO-funded hydrogen production and delivery projects at NREL as well. Dr. Din has over 15 years of experience in direct methanol, hydrogen polymer electrolyte membrane, and zinc air fuel cells at national labs and in industry. Before NREL, she also worked at 3 different fuel cell startup companies. She has also led an international working group to develop standard photoelectrochemical testing protocols for the DOE hydrogen program. While Dr. Din is speaking, as Chris mentioned, please feel free to type questions in the question box. We will be answering them at the end of the presentation. Please keep the questions focused on the technical aspects that Dr. Din can answer, these capabilities questions will be prioritized. So, Dr. Hewen Din, thanks for being here, and the floor is yours.
Thank you very much, Ben. My name is Hewen Din, and today I hope to convey to you what are the different resource node capabilities that we have in HydroGEN specifically for electrolysis and how you engage with the national labs quickly and effectively. Sorry. For those who don't know what the HydroGEN EMN is, it's an energy materials network that aims to accelerate the RD&D of advanced water splitting technologies for clean, sustainable hydrogen production, with specific focus on decreased material cost, intermittent integration, and durability. Within this EMN, we focus on 3 different pathways, both low and high temperature electrolysis, photoelectrochemical, and solar thermochemical, where hybrid thermochemical falls under that. This is a great picture of the group that was at the April workshop in April at Stanford, discussing advanced water splitting pathways. At this workshop, you can see there are many faces that are probably on this particular webinar today. We discussed about what are the challenges with these particular technologies and what suggestions and pathways and collaborations that we can do to resolve those, to help advance those issues. So the major outcomes that came out of the Stanford workshops are these outlined here. People agree that the detailed TEA and greenhouse gas emission analysis are important, and that the accurate TEA requires a strong understanding of full system requirements, and that's very important to emphasize there. When we define metrics, we need to define them well, and they can be connected to device and system level themselves. Furthermore, within these 3 pathways, there's a lot of cross-technology collaboration opportunities. These include materials challenges and opportunities between high temperature and stitch, including active materials and balance of plant materials. There's also overlaps in catalyst discovery and development needs that are common in both PC and low temperature electrolysis pathways. The membrane separation materials were also noted as a research need for all of these technologies. And hence, the HydroGEN EMN Consortium, these guidelines were used to establish HydroGEN EMN Consortium on advanced water splitting materials. So our main focus, as you can see, that we do need to look at different pathways, water splitting pathways, in order to reduce the hydrogen renewable cost. The production target for DOE here is less than $2 per GGE for production in general. I encourage you to go on the website to find out more information about our EMN, as well as all the capabilities on there that I will highlight today. I want also to highlight the different technology abbreviations that I'll be using within this presentation. This will be under advanced electrolysis. There will be LTE for low temperature, HTE for high temperature, and HT for hybrid thermochemical. I'd like to introduce you to my steering committee, the HydroGEN steering committee from 6 national labs. So the capabilities I present today come from these 6 national labs, and the pictures you see here in the names are all the people involved, the technical leads. I also have them online today to help me answer any questions that you may have regarding the capabilities at all the national labs. So here I will start talking about the advanced electrolysis status and technology in general. This map really just shows you that electrolysis, water electrolysis, is a worldwide effort. You can see that there are people all over the world involved in PEM electrolysis in this case, and alkaline as well as solid oxide electrolysis. Under solid oxide electrolysis, you can see there are 2 companies are highlighted here where they've already delivered some commercial products, one from Sunfire here and Toshiba. Has great potential for future stationary hydrogen production, but there's also some strong R&D activities that are needed. These are some names and pictures of the different PEM electrolysis that are being commercialized currently. As you can see, it's an international effort from US to Canada to Germany and so on. As you can see, they're also scaling up to megawatt systems, and there are challenges related to that as well. So although the PEM electrolysis in general are commercial and at the higher TRL, there still remain many technical challenges for PEM water electrolyzers, one of which is to be able to improve the stack performance. And these could be related to things like reducing the titanium dependence in the both bipolar plates and porous transport layers. Without these coated layers, there tends to be degradation. There's also a membrane need. We need thin membranes that are mechanically stable and also reduce crossover. And we also need better catalysts. The majority of the commercial products you see out there uses very high catalyst loading and hence they have very good durability. But when you start reducing that catalyst loading, that durability will definitely decrease, and so we need to explore and understand better how that works. Electrolyzers also have to be operate dynamically and flexibly, and also function well with startup and shutdown. As you can see here, it also operates at high temperature. So these are all unique to electrolyzers that need to be addressed. So on the HydroGEN capabilities website, you can see that we have over 80 capabilities from the 6 different labs. The links for the websites are shown there. So I'm going to start by talking a little bit about the different capability node readiness categories that we have, and it's unique to HydroGEN EMN itself. Through the review of different capabilities that were submitted to us, the steering committee review them based on different requirements. The nodes are not just an equipment, it is actually a tool, technique, and expertise that are unique to the national labs. And the categories themselves, we have 1, 2, and 3, as you can see here, and that's based on availability, readiness, and relevance to the advanced electrolysis, in this case, for this webinar. And it's not necessary, we're not taking into considerations expense and time commitment. So category 1 and 2 are the ones that I will talk mostly about today. The category 1 are the nodes that are fully developed and have been used for advanced electrolysis research. Category 2 requires some more development in order to demonstrate it in, or has not been demonstrated in advanced electrolysis. And category 3 nodes require significant development to get to that point. So overall, in HydroGEN, we have about 59 advanced electrolysis capability nodes altogether. 23 are in category 1, 31 in category 2, and 5 in category 3. You have to note that many of these nodes span different classification areas. As you can see here, we have 6 different classification areas, from analysis to computational tools and modeling, to characterization and synthesis, process to scale up, and system integration. So what this box here, or rectangular box here, means is that we have about 2 analysis nodes that are in category 1, 9 in characterization, and so on. Okay, and a lot of these nodes also span different technologies, and you may have seen this in the PC presentation that Adam gave last week as well, because they will span different technologies depending on, but they may have different readiness levels. So for node usage, you can use the projects that are being proposed, could use multiple nodes to leverage the national lab capabilities and to have a big progress and impact on your projects. So it depends on what you have already and what your proposal may look like, and you may already know how to synthesize a certain material, but you need some help with the national labs to characterize it, or you need some computational to help you, to guide you with some of that synthesis work. Or perhaps you know how to make catalyst powders, but you don't know how to integrate them together into an MEA, and we have those kind of nodes as well. Or you need help in how to do some techno-economic analysis, or you need help in how to scale this particular synthesis out into different processes and looking at the issues that goes with that. And we also have capabilities related to system integration. So in this particular technology, it covers all these different types of classifications. Note that not all types of nodes have to be used, though. Just really what your needs are, prioritize them to give you the biggest impact for your project. So I would start with the computational tools and modeling capabilities as listed here. You can see we have about 7 different capabilities that are in category 1, 2 in category 2, and 5 in category 2. Even though it's listed 2 here, there are some in here that are also in category 2, and count up to 5, and then 1 in category 3. So I've color-coded these according to whether they are multiphysics or ab initio types of computational tools or others. As you can see here, that many of the nodes span different technologies. For example, this one is a 1 for low temperature, while it's a 2 for high temperature electrolysis. Okay. So I am not a serious analyst, so I will rely on my experts here to answer any questions you may have regarding this. So I'm going to go through this quite relatively quickly. This first node here is DFT node from NREL. It is a 2 for both high temperature and low, category 2. As you can see here, it can help with electronic structure prediction, as well looking at defects in alloys. So you're interested in looking at doing a material design discovery from first principles. This capability can help you to do that. It has already been applied for PC, and hence, but it's not quite there yet for electrolysis. Now, if you want to look at interfaces and trying to figure out what's going on with the interface itself, this particular modeling capability from Lawrence Livermore could be very useful. You can look at the solid-liquid interface or electronic properties of the interfaces and electrocatalysis as well. So this capability has also been applied to PEC, but are being developed for low-temperature electrolysis. And if you want to look overall to see how to predict and optimize cell performance, you perhaps want to look at Lawrence Berkeley's, this is Adam Weber's capability. As you can see here, you can look at the whole system model itself by looking at the various different inputs to try to predict that. So they have extensive experience in this for both water splitting technologies as well as fuel cells. And it helps develop for specific materials and sets of conditions. And one last modeling one is another one from NREL, where again, at a higher scale, this capability enables you to look at the effect of materials, of components, to assess their performance and lifetime through a high fidelity modeling of a component design. So you want to look at the whole system in general and input in performance data to see how different things affect each other. So this modeling capability has been applied to fuel cell stacks and design as well as stitch. Okay, before I go into the other type of classifications capabilities, I wanted to give you just an overview, an example of the range of capabilities that we have in HydroGEN. This one I borrowed from NREL, where you can see that we have capabilities from synthesis, material synthesis, as well as ex situ electron characterization. We can scale up and make some MEAs, various different techniques here. We can also go higher scale with our roll-to-roll manufacturing process and also do some quality control on those films as well. We also can do in situ performance evaluation, both at a single cell level to stacks, as well as all the way to a whole system, as you will see. And we also have a hydrogen generation and dispensing capability here at NREL. So we start with the synthesis capability. As you can see here, there we have about 3 that are in category 1, and 3 capabilities in category 2, and 1 in category 3. The first one I'd like to talk about is the novel membrane fabrication development capability for low temperature electrolysis from NREL. NREL has been world class leaders in this particular research in synthesizing and fabricating polymer electrolyte membranes and ionomers for both PEM and AEM electrolyzers and fuel cells. You can see from the 2 here that we do both polymer synthesis, hydrocarbon and fluorocarbon polymer backbones, as well as looking at Tesla chemistry, as well as looking at ion exchange groups here. We also try to understand what the degradation mechanisms are of these particular polymers. We also can, NREL can also synthesize membranes and using variety of techniques outlined here, as well as develop different novel methodologies using our world-class custom-made dual fiber electrospinner that's shown here. This membrane or separator capability comes from Sandia. Their focus is mainly for alkaline membrane fuel cell, but I think they've also demonstrated this for high temperature, the hybrid thermochemical system. The advantage, of course, for alkaline is that no precious metal is used, and it's low cost. This is a picture of their membrane here that has shown over 2,000 hours of durability in an alkaline environment. The next capability is about catalysis. It's an NREL capability. As you can see here, there's a line that separates the left from the right. The left is all about synthesis. So NREL is capable of synthesizing our own catalyst for both PEM and alkaline exchange membrane electrolysis. As you can see here, the solid lines are constant mass activities, and this here is 0.3 amps per meter squared performance for iridium, and NREL is able to synthesize iridium alloys here that are about 10 times greater in activity than the standard state-of-the-art materials there. And show you that we can also characterize them in different methods, as well as test them in an MEA form. Show you the capability that we do both ex situ performance measurements as shown here. We've baselined a variety of different types of catalyst materials, and Sean Alita is the expert for this. He's also developed a technique to measure the surface area of both iridium and iridium oxide so that we can determine specific and mass activities. We've also correlated the performance of both ex situ and in situ in MEAs and done some carryout durability measurements. The next capability here is also from NREL. It's being applied to PEC, and it's being developed for electrolysis here. It's really to make model thin films. If you're interested in looking at a combinatorial types of materials using physical vapor deposition techniques listed here, but you can see that we can do different elements here. You can make metals, oxides, nitrides, sulfides, for example. You can do them different gradients, whether that's composition you're interested in, or temperature, thickness, and so on. This capability also has a whole suite of spatially resolved characterization techniques that goes with that, and as well as analysis. So a lot of these techniques, they can actually collect automatically, and then they also have analysis tool that will look at them the results themselves and to help you better understand what it is quickly. So I'm going to go next now. So you've made some catalysts. Now you want to figure out how to improve the process itself, or the manufacturing and scale up of it. So talk a little bit about two of the capabilities, one in Category 1 and one in Category 2. But all these capabilities are available on the website if you'd like to go in there and to read more about them. And at the back of this slide deck, which will be available to you, are also some other capabilities that we couldn't talk about today. The first one I'd like to talk to you about here is one from NREL. It's a high throughput approach to scaling up the PEM electrolysis electrodes. As you can see here, we can do make different types of electrodes, so depending on what we're interested in, doing combinatorially, different compositions or structures, gradients of different kinds, and we can also using different processing techniques that you can see here. This capability is from Idaho. It's able to make advanced materials for water electrolysis as well. As you can see here, it's also focused on development of electrode and electrolyte materials at intermediate temperature. Well, the previous one was more focused on the low temperature, although they've done some work on solid oxide materials as well. You can see the key features here is that they can do both range of work from material discovery to synthesis to characterization, as well as scale up. And they also have high throughput performance testing and characterization, as well as a suite of different characterization techniques here, including corrosion characterization. I'm going to go on now to our biggest classification of capabilities. It's the characterization capabilities. You can see there's many here, 13 in Category 2, 9 in Category 1 and about 2 in category 3. So I'll highlight a few of these. The first one is from NREL. This is the capability to be able to test in situ the electrolyzer performance and durability. The NREL has 3 tested systems. One is, and they've also done some benchmarking with leading research institutions and industry. You can see that they can test from single cells to stacks and all the way up to system components to about 250 kilowatts. These are some specs for the different types of test stations that we have. One particular good feature to add is that there's a 50, we can do it at high pressure, 50 bar. We also have the capability to do hydrogen pump option here, and AC impedance, as well as doing product gas analysis. This next capability is for the higher temperature electrolysis, and it comes from Idaho. As you can see here, they've also been doing, I think, $20 million invested in this particular capability. They have a whole suite of testing capabilities here for high temperature electrolysis up to 800 degrees Celsius. Looking at materials itself, as well as balance of plant materials, looking at the post-mortem analysis, as well as examining and understanding material performance and degradation issues. INL is the lead lab for high temperature electrolysis, and they have a range of capabilities, as you can see here, from button cells all the way to multi-kilowatt testing, all the way up to stack configurations. They have many test stations. They can do both a fuel cell mode as well as electrolysis mode, and lots of different post-test examination capabilities are listed here. As you can see, they can go all the way up to 1100 degrees Celsius for corrosion testing and different environments. I'll talk a little bit more about that. And this is the one, right? Yes. This one is also from Idaho, and I have a control environment effects laboratory that allows one to look at various different mechanical properties of materials. They can do mechanical testing here, crack growth, fatigue, creep fatigue, and so on, at various different environments and high temperatures. You can see you can do it at hydrogen atmosphere as well as a helium-rich atmosphere. They can do microstructural analysis and do fundamental mechanisms, trying to understand fundamental mechanisms as well. If you are interested in looking at the interface and looking in situ, you would want to look at this particular Berkeley National Lab capability, where you want to be operating a electrolyzer in situ to there's an operando approach here, where, as you can see here, you look at SAS as well as XPS. You can do all these types. They've developed this technique so that you can look at what's going on, these types of reactions and at the interfaces during operation. Berkeley also has capability, expertise in looking at ionomer itself. You can see here they can fabricate thin films and different approaches here to make different ionomers, as well as characterize them both at the thin film level as well as the membranes. And they have a suite of characterization techniques to look at the different physical and mechanical properties of the membrane, as well as the structural properties shown here. I'd like to touch on another characterization technique. This one is from Savannah River. They have a capability to look at the different electrolyzer components at high temperature. You can see that they have catalyst test stations that they can look at, and membrane test stations as well, and pressurized button cell test facility designed to look at about 130 degrees Celsius, highly corrosive fluids, and at high pressure. Now I'm going to go through the next few slides very quickly because they're all related to each other. Corrosion is one of the big issues in electrolysis technology, and I wanted to show you that we have a suite of different corrosion capabilities from all the different national labs. This one is from NREL. As you can see that we have capabilities to look at electrochemical corrosion as well as looking at weight changes and so on. We're looking at characterization techniques before and after, and look at the durability testing and post-mortem prolifinometry, as well as looking at some analytical techniques to look at the what comes out from corrosion products. This one, I believe, is from Berkeley National Lab. You can see here they have a lot of techniques that's listed here for electrochemical to ICP-MS and AFM to look at material characterization, degradation, and they also can help with some various protection schemes if we better understand what corrosion mechanisms are. And they've applied this to PC as well and developing for electrolysis. Similarly, Lawrence Livermore has a capability in corrosion that are similar, where they have different characterization techniques listed here to look at the surface morphology, looking at the chemical, identify the chemical activities, and looking at corrosion mechanisms to better understand what the corrosion mechanisms are and mitigate them. This one is a different one. It's the one from NREL where you can look at probing real-time and high throughput characterizations of the different materials. Looking, as you can see here, this is a cell that has different callus loadings, and you can see what the effects are by mapping it, doing various different imaging techniques that we have, and correlating that with the amount of callus that's actually on the surface. So it helps to map the composition and the properties of cell materials. System integration is our next classification of capabilities. First one I'd like to talk about is the one we have at NREL here. We've developed it over the years with FCT funding. You can see here there's a electrolyzer stack test bed here that have module components here. There's a pump here. The stack is over here. We have the dryer, a separator, and so on. You can see that. So they've done a lot of testing of large stacks, 150 kilowatt up to 250 kilowatts. And you can see there's the other specs that are here. This system is also used to supply our house hydrogen for fuel cell testing and work, as well as fuel our car stations, as you can see here. We have a hydrogen dispensing and generation system. This particular capability is also from NREL. It allows you to look at the integration of the different materials and looking at the balance of plan designs, specifically for high temperature and stitched electrolysis here. We go into economic analysis. I'm going to go through this quickly because Adam had talked about this quite a bit in his webinar, and note that most of, not all the projects will likely utilize these particular nodes. The first one is the techno-economic analysis from NREL. As you can see, we developed and support this type of work for DOE for many years. But there's also other tools that are listed here that are available to the EMN. We also have a TA type of analysis from Savannah River, I believe this one is. and it's based on the flow sheet development. As you can see, they develop a whole spreadsheet, a worksheet, and then figure out what are the different cost impacts on them. We also have a capability to determine the LCA, and this comes from Berkeley National Lab. And so if you want to look at more about the impact of the greenhouse gas emissions and the synergistic with TEA analysis here. Okay, that brings me to the end of the webinar. And for more information, you can go into our website or email us or contact any of the people that are listed here. But preferably, we'd like you to go through our website so that the entire steering committee can see our correspondences. And thank you very much. Oh, and just a plug, there is one more webinar coming up this week on Thursday, and that will be part 3 on the thermochemical or stitch hydrogen production. Okay.
All right, great. Thank you, Hugh, for the presentation. If you could go back a slide just to reiterate that the questions can be asked by typing into this question box. We have a few that I'll go over. Just to reiterate, please keep your questions related to the technical aspects of the nodes and the capabilities of the laboratories. Hugh is joined by the rest of the steering committee, which includes representatives from the 6 national labs, so they can help field questions related to those capabilities. So Hugh, to start off, we have a question here. The term advanced electrolysis has been used. What is exactly meant by that, and how is it different from regular water electrolysis?
That's a good question. I think we try to come up with a better term, but we haven't been able to do that. But advanced electrolysis really is inclusive of both low and high temperature electrolysis, and in some cases the electrolysis from the hybrid, not in some cases, but it also includes the low temperature electrolysis from the hybrid technology, thermochemical technology. Okay. Specifically, in regards to the high throughput experimentation thin film deposition, is this able to deposit uniformly on high aspect ratio structures, or is this purely a line of sight? It's the sputtering one? Is that, yeah, I think so. Let's see. This one, right? I think they're referring to this particular capability. This is line of sight capability. Yes, it's sputtering and post-laser deposition. But it's on an XY table here, as you can see, so you can move around and be able to do a gradient.
Okay, great. We have a couple questions relating to the state of the art of electrolysis. What is the maximum lifetime or state of the art lifetime in electrolyzers, and what electrolysis technology is state of the art if considered PEM or solid oxide field electrolysis cells or alkaline?
Well, I invite all the steering committee to comment on this, but I mean, I think different electrolysis are for different applications, and PEM electrolysis and solid oxide electrolysis are for different ones. But what is the durability currently? I think, I mean, we would like to get to beyond 50,000 hours. I think they perhaps you've reached 10,000 hours at least. Or more. What is it in solid oxide?
How do you define state of the art? I mean, you can link in things like performance and efficiency. You can link in how mature the technology is, etc. So it's kind of hard to say what is the state of the art. There are commercially available technologies for electrolyzing water, and then there are more research-oriented technologies that are still under development. But there are certain goals, of course, longevity and thermodynamic efficiency.
Does anyone else from the steering committee like to chime in? But as you see, though, as I mentioned before, the durability will decrease when we decrease the catalyst loading, because right now it's quite high for PEM electrolysis at least, and so that needs to be looked at.
Maybe one other comment concerning state-of-the-art. The reason for going towards higher temperature types of electrolysis technology are to reduce the electrical requirement for splitting water. And there are some thermodynamic efficiency gains that you can realize by doing that if you have an available heat source. So state-of-the-art also involves what your energy sources are that you're going to link the electrolyzer to.
So this is why this particular EMN is looking at different pathways and see which one will help us reduce the cost and which one is good for which application.
Great, thank you. I have a question here for DOE folks. If anyone else is on the line, we've gotten this a few times. Can national laboratories who are not part of the EMN be on proposal teams? Do we have anybody? Is Eric on?
Yeah, Ben, do you hear us?
Yes,
can you hear us, Ben?
Yep.
Yeah, this is Eric. Thanks for asking. You know, we get this question quite often, and if for those of you who've been tuning into the webinar series on our HydroGEN EMN, you've heard this topic come up and addressed. We had been putting it off originally till the FOA language came out itself, but it's come up so often that we've put it out there that it's expected that national laboratories that are non-parts of the EMN are not expected to be excluded from proposing. So hopefully that helps address the concerns or the question that keeps coming up in that area. Again, I do refer you to the specific FOA language itself, but there's not an expectation that non-consortium laboratories will be excluded from proposing.
Great, thanks, Eric. We have a couple questions since the DOE is speaking. We have a couple questions relating to certain specific technologies. For example, metal-supported cells for SOEC, or also self-standing electrocatalysts. Do we prefer self-standing electrocatalysts or powder form catalysts?
Right.
And I believe the answer to that is we are open-minded, and that will become more apparent when the FOA comes out. We're mostly focused on what will be best to meet the targets, and no specific technology, I would say, is being sought after or excluded. Is that correct, Eric?
Yeah, I put it another way. I think this came up again with the previous webinars. Looking for specific topic areas. Again, when the FOA comes out itself, that the language will be a lot more clear. But just in broader perspective, that the purpose of the EMN project is really looking for materials innovation. Materials, as long as an impact on the technology that the materials innovation is addressing can be made clear in terms of how it could lead to the cost targets of the program. That's the broader picture we're looking for. Materials innovations and the potential impact on cost reduction to meet DOE cost targets. So that's the broad picture, and more specific language will be available when the FOA is released.
Okay. Now a question for the technology experts. Are there any capabilities or nodes that could be used in high-pressure electrolysis?
Well, INL has done high-pressure, high-temperature electrolysis studies in the past, so there's one possibility there.
And how high is high?
Right.
We're showing.
We've gone as high as a couple hundred PSI.
Okay.
So, at the INL.
Right.
Yeah, at NREL we can go to 50 bar with respect to the short stacks and the small stacks. And I think our larger system, I don't know what the output pressure is there, because we're obviously pressurizing it for vehicle filling pressure, but that's not, producing at pressure. So 50 bar with respect to research size is our highest pressure that we can go to.
Okay. Great, thank you. And related to definitions of high and low, we have a question of what are the temperature limits for low temperature and high temperature electrolysis when we're using these terms?
Well, the temperature limit for low temperature electrolysis is based upon the membrane, I assume. In terms of high temperature electrolysis, from a thermodynamic standpoint, the higher the temperature, the better, but you suffer trade-offs in terms of material durability. So there seems to be a focus of an operating temperature around 800 degrees centigrade for oxygen conducting high temperature electrolysis technologies. There are some efforts also going on proton conducting, let's call it high temperature electrolysis, but trying to bring that temperature down to temperatures like 500 degrees centigrade, with the gain being that material durability might improve, but you might suffer some thermodynamic inefficiencies. So there are trade-offs there.
There's a range for solid oxide as well, right? 800 is one of them, the other one perhaps between 200 and 600 degrees Celsius?
Yeah, there's a whole range of temperature. Of course, the kinetics go down with lower temperature. The efficiency goes down with lower temperature, but of course, durability to a point improves. So
I think for PEM electrolysis, most people test about 70 or 80 degrees Celsius, but there are also efforts going to higher temperature membranes above 100 degrees Celsius.
So for PBI type membranes or so, you could imagine that the temperature ceiling there is about 140 C or so. And that's really only dependent on the heater, if you use an insulating heat jacket or other small details that help you to get up to that temperature. So I don't see a real limitation there up to 160 C or so. That should be all manageable.
All right, great. Thank you, everyone. We are running low on questions. If you have any last-minute questions, please include them now.
Someone wanted me to put up the website.
Well, one question I was waiting till the end. I'm not sure if this is the end or not, but there was a request for exactly what you have up, which is the relevant websites where we can get more information. Good call.
I saw that.
there was a question about leakage current in in electrolyzers. I don't know about low temperature electrolyzers, but yes, you can have leakage current in high temperature electrolyzers, and it's not necessarily an inefficiency. As a matter of fact, there's some people theorizing that it might actually be beneficial to have some leakage current in high temperature electrolyzers, but I thought that was an interesting question that someone posed.
Yes, there we are. Great, thanks, Carl, for picking that up. I missed that in the list. Another question, what type of research capabilities are available for electrolysis steps in hybrid stitch cycles?
What capabilities are available for hybrid? Did I hear that correctly?
Yeah, for hybrid.
I highlighted a few here. One of them was the testing capability, characterization itself. One of them was a TA one, and I know there was 3 of them. Can't remember the other one.
The other one is the Savannah River capability, where they're looking at the electrolyzers of splitting or creating as part of the electrolysis to make the thermochemical cycle to make the sulfuric acid, which is part of that thermochemical So,
You can stop me.
Hybrid sulfur.
yes, it's typically called the hybrid sulfur flow sheet for making hydrogen, and probably need to put that.
Yeah, that was the TA one that was under analysis, and under characterization, there's this one. So anything that has an HT on it, which is hybrid thermochemical, are the ones that's related to that particular technology. And there are more on the back as well. Let's see. This
one here. So this one is certainly where they're able to test these membranes and catalysts in these very harsh environments that are reminiscent of many of these thermochemical systems. And so here they have a capability where they're set up to deal with those harsh environments, those corrosive chemicals, and do the handling and do the testing and do the characterization of their the things that are being tested. So.
Yeah, one of the things they've been concentrating on is sulfur pass-through.
And this is the other one from Savannah River.
So this one here is reporting to the analysis tools and capabilities that they have for this overall flow sheet here. And so I think you'll see some of this is in a crossover with also what will be presented here at the next webinar, which is dealing with the stitch. You see some of these different processes that show up in these two different areas. This one here, it happens to be one of the leading type of hydrogen generation technologies here that is being also developed in somewhat a worldwide sense. So it seems to be leading out in hydrogen production where you're doing water splitting, and it often involves an acid in the system.
Concentrate sulfuric acid. Any other questions?
Yes, we have another question. This one comes up. Also, when is there an estimate on when the FOA will be made? And because I've heard this answered enough times that I think I can answer it. The short answer is soon, but you can also get some clues. You can get some clues of when, based on looking at previous years of when we sent out the NOI, and the FOA will be working on a similar timeline. If there are no further questions, we can probably wrap up.
Hey Ben, one more quick response to that final question as well. And since we're about to wrap up, it's just a good time to remind everyone that this is a good time to be exploring the website and working on talking with people that you'd be interested in possibly collaborating with to develop your ideas and your innovations, and evaluate how you can best leverage some of the resources that are available in the consortium. Once the FOA is public and announced, there will be restrictions on the certain types of communications, so we really do encourage people to take advantage of the time between the NOI and when the FOA is announced to really get to know each other and start to explore the opportunities. This, again, if someone just asked a question also specifically related to that, and when the FOA does come out, there will be language in there that has restrictions on what the types of communications will be, and we really ask everyone to pay close attention to that.
Great, thank you. If Eric, if you have nothing else, and it looks like we are out of questions, thank you, Hewan, and the rest of the steering committee for answering all the questions and presenting. Maybe you want to pull up the websites as we leave, or maybe Chris has some final housekeeping information.
Sure, Ben, I can take it from there. Thank you very much for your moderating. And Hewan and panelists, thank you very much for your contributions to the questions and answer, and for the great presentation. Eric, thank you as well. If we didn't get to your question, or if you have any subsequent questions, please feel free to email the presenters directly, and they will try and respond to you in a timely manner. Hewan, if you want to throw up the thank you slide, maybe at the end there.
Oh, Okay.
I can get us out on that. This one's fine too. I'd like to thank everyone for calling in. I remind you that the webinar, excuse me, and slides will be available online at the Fuel Cell Webinars website in about 10 days. Also, I encourage everyone to sign up for our monthly newsletter, which is going to include information and registration for upcoming webinars. I'll remind everyone that on this Thursday, November 17th, we'll be hosting part 3 of the HydroGEN Consortium webinar series, and that will cover solar thermochemical hydrogen production, aka STITCH. So thank you everyone for calling in, and we'll talk to you soon. Bye-bye.